And welcome, function folks. The last hurrah for logs, ROC logs, rate of change. 3-minute review first. Kind of a funny looking equation here. There's like a double log going on, but how do we do this? Well, there's only one x there. We want to get to the x. How do we do that? Well, opposite operation, and I can't undo the log base 9 until I undo the log base 2, so that's the first step. Log base 2 of both sides, this will cancel each other out, and I'm left with just the log base 9 of x. And on this side, 2 to the exponent minus 1 is 1 over 2 to the exponent positive 1, right? That's the exponent rules from grade 11. All right, dandy. Next step is opposite operation of log base 9 is exponential function base 9. Running out of room. And then I got this cancels each other out, and I'm left with x equals 9 to the exponent a half. Well, 9 to the exponent a half, remember your exponent laws. The number on the bottom is the root, number on the top is the exponent, 3. Good old 3. And that's it. I could substitute it back in there, but it does work. Number 2, leading into today's stuff, write any true statement about the IROC of y equals a to the exponent x. And this is meant to just sort of get us starting to think about it. An exponential function, we might be tempted to think of it like this, right, where this is 1 and then this is the point 1a, and over here we got -1 and 1 over a, so there's the. So we would be tempted perhaps to say that, the IROC, remember, is the tangent. I think, oops, wanted a line there. There we go. It's tangent, and I can slide that along, and looks like wherever I go, I'm going to have a positive tangent line, right? Positive, 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 positive. So I might be tempted to say A is, the IROC, rather, is always positive. Well, is that always true? What happens if what happens if it's a decay function, right? What happens if A is a decay function? Well, then the tangent lines are all negative, right? Yeah, so the IROC is greater than 0 is true if A is greater than 0. If the base is greater than 0, the IROC is greater than 0, which means F is always increasing, right? Increasing. Remember, positive IROC meant the graph was going up. But, the IROC would be less than 0 if A is less than 0, and F would be always decreasing. This is for a decay function, right? Decay function. This one is for a growth function. And notice that a very similar thing, and this is really what we wanted to talk about, was what happens for the log function. Well, the log function is quite similar, right? We think of our log functions as, going through this point and then going like this, basically the inverse of this green one, right? This is y equals log base a of x, and it's always positive, right? IROC is greater than 0, right? Because if I got where's my tangent line here? That's my decay function. Here's my tangent, and I can get, wherever I go, wherever I find the tangent function, it's always going to be positive. If I could grab there's my tangent, right over here. It's always going uphill. That's if the base is greater than 0. And again, F is, because the IROC is positive, F is always increasing. But what happens when I flip this one? When I flip this one, the very same thing happens. I flip this one, I end up with a graph that looks something like that. It still goes through that same point, but it's always decreasing. The IROC is less than 0 if A is less than 0. Not A is less than 0. If A is a fraction, whoops, holy moly. If A is a fraction, if A is less than 1, of course it's not going to be negative. We can't have negative bases. That would mess everything up. Go fix that. Go fix that in your note. What we're thinking of is a decay function, right? So F is always decreasing. And it was okay if you wrote some other true statements, like I'll bet you some of you became creative and said something like this, which is true. You thought for y equals a to the x, as x goes to negative infinity, what happens to the IROC? So if I think of way out here and I draw a tangent line out there, what's true about the IROC? Well, the IROC is getting closer and closer to 0. And in fact, that's true for the IROC here is getting closer to infinity for the log function. All right, and there's lots of true statements that you could have written there. Dandy. Let's keep moving on here. 3-minute review 2. Which statement is most accurate in describing the graph of f at x equals log base 2 of x? And that's it right there. So let's see. F is increasing. We already mentioned that, right? We already sort of decided for a base that's positive, both the exponential function and the log function are always increasing. So the function itself is always increasing. But what's going on for the IROC? It says the IROC is always positive. Now that's true, right? We said, oops, when we were thinking about the IROC of the log function, we said that it's always positive if the base is positive. So this is true, and this is true. The IROC is always increasing. This isn't true. Have a look. That right here, I might have, I don't know what it is. I suppose I could calculate it, but this might be an m of, say, 2. The slope of this tangent is 2. But if I move further along, what might this slope be? This might be a slope of 1/3 or something. Who knows? I'm just guessing here. But that means the slope, the IROC, I don't know, this might be like 0.5, and this is maybe around, who knows? Doesn't matter. What was that? That was maybe 3.5. At the IROC went from being 2 to 1/3. It went down. So this isn't true anymore. Oops, this one's not true, rather. This one might be true. So is this statement A true? This is not true. But we said these two are true. The IROC is always decreasing. Certainly it did for the two that we mentioned. If we go further along, what's going to happen? Right? Big, smaller, 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 smaller. This is true. This is true. This is true. This is not true. The IROC isn't negative. It's always positive. The slope is always positive, but it is decreasing. So it's B is the correct answer. So this is a common thing, especially in when we start moving towards calculus, is we get goofed up between the function itself, its rate of change, and in fact, we're all talking about the rate of change of the IROC. We're talking about the rate of change of the rate of change here, and although it's not real important in our course, it starts to become more important in calculus class. Phew, okay. I didn't think IROC was that difficult. Let's get into an example. And this is going to be boring old stuff that you're used to, but we've got an application here. The global population is given where T is the years since January 2008 and P at T is the population of billions of people. Estimate the IROC in 2014. So remember, the instantaneous rate of change is just P at T plus H, I guess, or A plus H, depending on what kind of formula you want there. P at T over the H. And here T is the number of years since 2008 is 2014, subtract 2000, that's 6 years. So our T value is 6 years. Our H is whatever we have patience for, but we've sort of settled on, we kind of like 0.01 because it's pretty small interval, but not too small that we've got a million decimal places. And so our value, and we could do this in the margin over here, but and that's P at 6, and then I'm going to P at 6.01 over there. I'm actually going to do this right in here. So P at 6.01 is this, but I'm not going to calculate this over here. I'm just going to do this all in one step. 6.7, 1.019, 6.01. What I'm arguing, what I'm suggesting here is that we can put this expression into our calculator in one step, and certainly it should be. This is actually an easier calculation than when we went back and did rate of change of rational functions, was maybe the worst. You jam that into a calculator and you get, what did I get? Where's my, I had this along here somewhere. Where was it? It was 0.141. What are the units here? 0.141. Well, this value is in billions of people, right? Billions of people per, well, what's the T change here? The T change was years. So billions of people per year. Which is scary, right? This is 141 million people per year. Right now, the planet is growing by 141 million people per year. What's that? That's about a half the size of the United States, right? The United States is around 300 million. So every year, the planet's population is growing by 141 million people. Just all of a sudden, half the United States appears on the same blue dot in space. A little bit scary, a little bit frightening. Sweat. Question. Isn't it just 1.9%? Isn't that the answer? But remember, this function is in number of people. Probably, if I calculated what the population was in January of 2014 using this formula, it would be going up by 1.9% per year. Okay, and in fact we can do that, but this IROC calculation sort of takes care of that. So don't get confused in the function value going up and the percent that it's telling you, right? That's an increase of 1.9%. All right, the next and last example of the chapter is coming up in part 2.